You are listening to The Vocal Technologist. Spoken tech for your ears.
You spend weeks, absolute weeks, building the perfect data dashboard. You're tweaking every single chart. You're formatting the axes so they align perfectly. You get the tooltips looking properly sharp.
Oh, and you do all the stakeholder interviews?
Right. You do the interviews, you wrangle the data pipeline, you finally hit publish, and you send the link out to the wider organization. And what happens? Absolute crickets. Nobody looks at it. It just sits there on some corporate portal and rots. And then the CEO just asks you for a spreadsheet anyway.
Look, it is a painfully common reality. The dashboard graveyard is vast, and honestly, it is full of incredibly well-intentioned engineering.
It's exactly like an abandoned gym membership. You pay for it, you feel good about having it, but you never actually use it. I'm stepping in as the voice of Vocal Technologist, basically your tech-savvy mate here, to pull apart what is actually happening in the data world.
And there is a lot happening right now.
Massive amounts.
Yeah.
We are going on an exploration to look under the hood of modern architectures. We are moving from the death of traditional dashboards all the way to autonomous AI agents writing their own documentation. Our mission is to unpack how massive engineering teams are completely rewiring their data plumbing to survive the AI era, and why the tools you relied on might be obsolete faster than you think.
We'll get into everything from semantic layers to fixing critical bottlenecks at hyperscale.
Exactly. So let's start at that surface layer, the humble dashboard. Why is it facing an existential crisis?
Well, the underlying issue is that human attention is the absolute bottleneck in any business. Most dashboards die unused because organizational attention constantly shifts.
They move on to the next shiny thing.
Spot on. A dashboard is usually built to answer a very specific, burning question that leadership has at one particular moment. But an agile business moves fast. Teams move on to the next fire before any sustained value or, maintenance of that dashboard ever materializes.
So it just becomes a short-lived artifact of past priorities, not an actual durable decision tool.
Yeah.
Exactly.
I mean, think about your own Slack channels. Someone is always asking a new, hyper-specific question that your static dashboard was never designed to answer. And the technology itself is pushing dashboards out the door. The engineering breakdowns are predicting that traditional business intelligence tools are becoming largely obsolete.
Yeah, large language models are simply handling natural language queries and charting much better than traditional BI tools ever could.
Wait, really? Like, better than the bespoke tools?
Oh, absolutely. The prediction is that the modern stack is collapsing into just 3 layers. You've got storage, compute, and context. Because of this, traditional extract transform load vendors are facing massive disruption.
Right.
We are seeing data engineers shifting away from being pipeline builders. The new mandate is to become a context curator.
A context curator, right? Because apparently having an AI tell you your metrics are bad hurts slightly less than reading a chart yourself.
That's one way to look at it. But seriously, it changes the entire profession. Even data visualization is becoming commoditized by AI. It's shifting from this highly specialized, almost artistic craft to generalist work. The AI removes so much of the manual effort that used to make building those visualizations, well, enjoyable for analysts.
It points to a much broader reality, though. Knowledge is only valuable when it is applied. Static dashboards simply cannot keep up with dynamic, ad hoc business queries.
Give me an example of that.
Well, say an executive wants to know why revenue dipped in a specific region. A static dashboard might only give them the top-line number. They then have to wait days for an analyst to build a new view.
Which is infuriating for them.
Exactly. But an AI agent with the right context can answer that dynamic query instantly. But that relies entirely on the AI actually having the correct context.
Yeah, and that's the scary part. If we're just letting large language models query our data directly, we run into a massive wall. How do you stop them from completely hallucinating the numbers? Because I reckon an AI confidently presenting completely fabricated revenue figures to a board of directors is a fast track to everyone getting fired.
Oh, straight up. That is the exact problem the industry is wrestling with right now. DBT Labs ran a fascinating benchmark comparing 2 different approaches.
What did they look at?
They looked at raw text to SQL, which is where a language model generates database queries directly against raw tables, versus querying through what we call a semantic layer.
Okay, let's reason this out for a second. If an AI hits a raw database, it sees a column named something obscure like Rev Final V2 actual exclude test.
A classic naming convention.
Right, terrible naming. A human analyst knows they need to exclude certain test regions or apply specific filters based on tribal knowledge passed down through the team. And AI doesn't know any of that. It just guesses based on the column name. So I'm guessing the semantic layer sits in the middle, acting like a dictionary.
It's much more powerful than a dictionary. The semantic layer is essentially the onboarding manual and the compiler for your new AI analyst.
Oh,
Even the most advanced LLMs fail when querying raw tables because they lack that tribal knowledge. The semantic layer delivers much higher accuracy because it provides clean, predefined business metrics.
so it's about machine-readable governance.
Spot on. Tools like RealMetrics SQL are creating native layers where business metrics are defined exactly once. They compile simple metric queries into highly optimized database SQL.
Right, because if your sales department and your marketing department calculate customer acquisition costs differently, the AI is going to get confused. It'll give conflicting answers depending on who asks.
Which happens all the time in large orgs.
Yeah. So the semantic layer eliminates that metric drift. It enforces a strict rule that says this is exactly how we calculate revenue, period.
But wait, let me push back a bit here. Is this semantic layer stuff just a fancy way of saying we need to write better descriptions for our columns? Like, are we just adding more bureaucracy? I get the skepticism, but no. It's fundamentally different. This is completely changing the hiring market for engineers. Business intelligence interviews are shifting away from classic SQL and dimensional modeling.
Really?
Yeah. Now, the real differentiators are governance, semantic layers, and AI-safe analytics. Interviewers want to know if you can enforce data contracts and ensure AI agents are querying governed semantics instead of raw warehouse tables.
Ah, I see.
Because in business, guessing is catastrophic. The semantic layer removes the guesswork entirely.
Okay, so you lock down the semantic layer, the data is governed, the definitions are bulletproof, and your AI isn't guessing anymore. Once you have that safety net, engineering teams are setting AI agents loose to do the heavy lifting in the code base. But letting agents run autonomous workflows introduces a terrifying new set of problems.
It really does. We were talking about agents unbound and the hidden technical debt they create. The shift from simple text generation to agentic engineering is profound.
Because it's not just a chatbot anymore.
Exactly. We are seeing coding agents massively outperforming traditional retrieval augmented generation, or R, on long context tasks.
Traditional RA is basically a glorified keyword search, right? You fetch relevant text chunks based on semantic similarity and feed them to the language model so it can answer a question.
Correct. But the right answer in massive enterprise systems is rarely just about finding a similar paragraph of text. It's often a structural navigation problem.
Meaning you have to actually dig through the system.
Yeah, it depends on finding the right section, the right table, or the right path in a complex hierarchy. Coding agents solve this by externalizing their reasoning into executable actions.
Wow.
They actually use file systems and search commands to iteratively explore massive repositories. They're not passively reading, they're actively digging, making mistakes, reading error logs, and trying new paths.
Which sounds incredibly powerful until you realize what happens when you deploy that at scale. Think about your own internal systems for a second. The documentation notes that there's a hidden technical debt to agentic engineering. Agents are very easy to build locally on your laptop in an afternoon, but they're incredibly hard to run safely at production scale.
Oh, building the agent itself is the easy part. The core burden sits completely outside the agent.
Like the infrastructure around it?
Spot on. We are talking about centralized integrations, live runtime context, human-in-the-loop controls, observability, and orchestration. Platform teams need standardized controls early.
Because if you don't have them.
Without them, you face massive risks of data exposure, or you might end up with runaway cloud costs because an agent got stuck in an infinite loop querying a massive database.
I want to highlight something properly wild from the engineering write-ups. Meta built a pre-compute engine using a swarm of over 50 specialized AI agents. 50 of them.
Yeah, that is a huge deployment.
And they set them loose to map out the tribal knowledge across their massive data pipelines. They have these agents generating context files that capture non-obvious patterns, dependencies, and undocumented conventions, which, yeah, is exactly as terrifying as it sounds, setting 50 AI agents loose in a massive corporate code base to figure out what the human engineers forgot to write down.
It is a brilliant, if slightly daunting, solution to a universal problem. But Meta treats these agents as a compass rather than an encyclopedia.
Right, they're pointing the way.
Exactly. They aren't trying to document every single line of code. They are highlighting failure modes and module purposes. If we analyze the broader pattern here, This agentic tech debt is perfectly mirroring the historical machine learning tech debt crisis from the early days of model deployment.
Oh, I remember that.
Back then, everyone realized that training a machine learning model was only 5% of the work. The other 95% was the infrastructure to serve, monitor, and contain it. We are seeing the exact same cycle with AI agents, but moving at a much higher speed.
So if you don't have those guardrails and orchestration layers in place, your helpful AI agent might just decide to drop a production database while trying to figure out how the billing module works.
Exactly.
But even if you perfectly contain your AI agents, there's a physical limit to all of this. Your autonomous agents and pristine semantic layers will instantly crash if the underlying storage pipelines degrade.
That is the foundation everything rests on. You can have the smartest AI in the world, but if the database takes 10 minutes to answer a question, the entire system is useless.
It's game over.
Yeah. We have to look at the unsexy infrastructure problems silently killing performance. A prime example is the small files problem in Delta Lake streams.
Let's unpack that. High-throughput Delta Lake streams are supposed to handle massive amounts of data. What is actually going wrong under the surface?
Well, these streams can silently degrade due to the continuous accumulation of millions of tiny files. Your pipeline status dashboard might show everything is perfectly green, but under the surface, the system is choking on its own metadata.
So it looks fine, but it's dying.
Spot on. Query latency can suddenly jump tenfold, and storage costs rise dramatically because of how the processing engine handles those files.
Let me try to put an analogy to this. Imagine you're trying to find a single receipt for your tax return. But instead of someone handing you a neat filing cabinet where everything is sorted into large folders, someone dumps 1 million individual sticky notes onto your desk.
That captures the chaos perfectly. And to take the analogy further, imagine you have to read the serial number on every single sticky note before you are even allowed to look at what is written on it.
Oh, that sounds like a nightmare.
It is. That is exactly what Apache Spark is doing. It spends all its compute time reading file metadata rather than processing the actual data you care about.
Right. If the sticky notes are the problem, logic dictates you either hire someone to constantly glue them together into bigger pieces of paper, or you stop writing on sticky notes entirely. How do engineering teams actually fix this when the dashboard is telling them everything is fine?
The traditional fix is deeply operational. Engineers need to schedule the optimize command on recent partitions to manually compact those tiny files into larger ones.
So that's gluing the sticky notes together.
Exactly. They also need to use the vacu im command to delete tombstones, which are records of deleted files that still take up space. But there are brilliant architectural solutions emerging. A system called Duck Lake introduces a concept called data inlining.
Data inlining. So does Duck Lake just refuse to write the sticky notes?
In a way, yes. It elegantly solves the problem by storing small updates, like inserts or deletes that fall below a certain size threshold, directly in its catalog database.
Wow.
Yeah, it completely avoids writing them as tiny Parquet files to object storage in the first place. This unlocks efficient, low-latency streaming workloads without needing constant, heavy compaction jobs.
That is properly clever. It just bypasses the bottleneck entirely.
Yeah.
But Delta Lake isn't the only place we're seeing underlying systems melt down under pressure. Look at what happened to Datadog. They had a metric summary page that hit a 7-second latency.
Which is unacceptable.
7 seconds to load a page in a monitoring tool is basically an eternity. People start refreshing the page, which just makes the problem worse.
It's entirely unacceptable for an observability platform where speed is the entire product. Datadog had to fundamentally redefine their data replication architecture. The root cause was their reliance on Postgres.
And Postgres is usually rock solid.
It is a fantastic relational database, but they were using it to perform expensive search-style joins across 82,000 metrics and 817,000 configurations. Postgres was simply failing under that specific type of load.
Right.
The CPU was spiking because relational databases are built for transactional consistency, not sweeping search queries across massive cardinalities.
But you can't just turn Postgres off or migrate the entire company overnight. So how did they untangle that mess while the system was running?
They stopped querying Postgres directly for those search workloads. Instead, they moved to streaming changes via change data capture. They used a tool called Babysium to read the write-ahead logs of the Postgres database.
Let's break down the write-ahead log.
Yeah.
That is basically the database's internal diary, right? It records every single change, every insert, update, or delete before it even makes it to the main table.
Yes, that's exactly it.
So by reading that log, Debezium is essentially eavesdropping on the database without actually interrupting it or slowing down the query performance.
That is the exact mechanism. They capture those updates in real time and buffer them using Kafka. Kafka acts as a massive shock absorber, lining up the changes safely. They then serve the actual search queries from a dedicated downstream platform.
Brilliant.
But to make this asynchronous replication safe at massive scale, they had to ensure data consistency. They did this by implementing a backward-compatible schema registry using Avro.
Right, because if an engineer changes the structure of the data upstream, maybe they rename a column or change a data type, and the downstream search platform doesn't know about it, the whole pipeline breaks.
Exactly. Chaos.
The schema registry acts as a strict translator to make sure everyone agrees on the format. It is incredible how much unsexy plumbing is required just to make a summary page load fast.
It highlights a universal truth in engineering. The closer you get to hyperscale, the more you have to abandon off-the-shelf solutions and invent entirely new architectures.
Which means we need to talk about the absolute masters of hyperscale, Netflix. When you fix the small files and you untangle the pipelines, you eventually hit the absolute physical limit of scale. We need to explore how Netflix is completely inventing new architectures just to make search and caching possible. Let's look under the hood of their multimodal video search.
Netflix built an incredible architecture to surface key moments across hundreds to thousands of hours of footage. They had to replace brittle keyword search with AI-driven retrieval. They were indexing characters, scenes, dialogue, and vector embeddings all simultaneously.
This blew my mind. Keyword search is brittle because if someone tags a scene as car chase and you search for auto pursuit, you get 0 results. So they're using AI to generate semantic meaning. But to actually map that out, they're segmenting video using overlapping temporal segments, and they bucket everything into 1-second intervals.
It's a massive undertaking.
Think about the sheer absurdity of the back-end compute power needed. They are processing thousands of hours of video into 1-second buckets, just so a producer can search for a very specific scene where a character says a specific word while standing in the rain. How do you even store a billion 1-second buckets without the system collapsing?
The engineering required to maintain that as a single source of truth is staggering. They use Cassandra for high-throughput annotation storage because Cassandra is brilliant at handling massive volumes of fast, messy writes.
Okay.
Then they use Kafka for asynchronous processing to line up those writes, and Elasticsearch for the actual real-time search queries. They maintain consistency using composite key upserts.
Let's define composite key upserts. A composite key is just a highly specific address made of multiple parts, like the video ID plus the exact timestamp.
Yeah.
And an upsert means update or insert.
Spot on.
So if a new AI model spots a coffee cup in frame 400, it just overwrites that exact address without creating a messy duplicate record.
That ensures the 1-second buckets stay perfectly synced without ballooning the storage with duplicates. But what is perhaps even more fascinating is how they handle the resulting query load.
Yes, the caching layer. Because if you have all that data, you do not want to run the exact same massive search query twice. Compute is wildly expensive.
Very true. Netflix uses Apache Druid for time series analytics, but they built a custom interval-aware caching layer in front of it to stop the system from recomputing the exact same time series question.
Caching sounds simple on the surface. You ask a question, you save the answer. Next time someone asks the question, you give them the saved answer. But caching time series data is notoriously difficult because time is always moving forward.
Right, the window shifts.
Yeah. If I query the last 24 hours of video metrics at noon, and then you asked for the last 24 hours of metrics at 12:05, the query window has shifted by 5 minutes. A traditional cache would see that as a completely new query, miss the cache, and hit the database again, wasting massive amounts of compute on data that is 99% identical.
Exactly the problem. So their interval-aware caching intercepts the queries at the router level and parses the actual structural meaning of the query. It stores the results in fine-grained time buckets using Cassandra.
Let's use an analogy here. It's like looking at a physical train timetable at a station. Instead of the station master printing a completely new massive timetable every 5 minutes because one single train was delayed, they just put a tiny sticker with the update and slap it over the old specific time slot. They're stitching the past and the present together.
That is precisely how it functions in milliseconds. When that second user queries the data at 12:05, the system recognizes the overlapping window. It serves the cache data for the settled intervals, the massive chunk of historical time that hasn't changed, straight from Cassandra.
Great.
Then it only fetches the missing recent tail, those new 5 minutes, directly from Apache Druid.
That is just elegant. It stitches the cache data and the fresh data together on the fly.
It is a masterclass in computational efficiency. They also implement gap-aware merging and exponential time-to-live protocols.
What does that mean in practice?
Exponential time to live means the older the data is, the longer it stays in the cache because historical data rarely changes. By only fetching the missing recent tail, Netflix balances extreme freshness with massive computational savings. They aren't just throwing more servers at the problem, they're fundamentally changing the mechanics of how questions are asked and answered.
It is wild to step back and look at this entire journey. We started with a humble dashboard, sitting rotting in a corporate portal because human attention shifted away. We explored how data visualization is getting commoditized and how the semantic layer is the absolute critical onboarding manual to stop your new AI from hallucinating revenue numbers to the board.
It's been a massive shift.
And then we looked at the terrifying reality of 50 AI agents roaming through Meta's code base and the massive platform engineering debt that comes with autonomous orchestration.
Not for the faint of heart.
Definitely not. And then we got into the unsexy critical plumbing, bypassing millions of tiny sticky notes in Delta Lake with data inlining, moving Datadog off Postgres to write-ahead logs in Kafka, all the way up to Netflix, building bespoke interval caches to stitch time together for 1-second video buckets.
It demonstrates clearly that the AI era is not replacing the need for deep data engineering. It's demanding a much more rigorous foundation. The surface layer is becoming automated, but the infrastructure layer is becoming exponentially more complex.
Which leaves me with a final, slightly provocative thought for you to mull over. If AI agents are already writing our documentation, if they're already querying our semantic layers and navigating our file systems autonomously, how long is it until the AI is the one sending angry messages on Slack complaining about our messy data pipelines?
That is a sobering thought. The machines might be our toughest stakeholders yet.
Something to keep in mind for your next architecture whiteboard session. I hope this exploration gives you a massive advantage when you're untangling your own systems, and that you keep vocal technologists queued up for the next one. Catch you next time.
Spoken Tech for your ears.